Tonight I want to take you somewhere extraordinary, somewhere that exists at the very edge of what we thought we knew about reality itself. It's a place where the rules we've always trusted begin to blur and bend, where a single particle of light can somehow be in two places at once, not just for a fleeting moment, but perhaps forever. I know how that sounds impossible, like something from a dream or a story we might tell ourselves when we're half asleep. But this is real. This is what scientists have discovered in the quiet corners of their laboratories, working with lasers and mirrors and detectors so sensitive they can count individual photons as they arrive. Before we begin this journey together, I'm curious about where you are right now. Perhaps you're tucked into bed in London, where the rain is gently tapping against your window, or maybe you're in Tokyo where the city lights are just beginning to dim, or somewhere in New York where the night is settling over the skyline like a soft blanket. Whatever time it is where you are, whether it's midnight or 3 a.m. or that peaceful hour just before dawn, you've found your way here to explore one of the universe's most gentle mysteries with me. If you find yourself drifting along with these ideas, feeling that quiet pull of curiosity mixed with the approaching edge of sleep, perhaps you might like to follow along for more of these cosmic journeys, more nights spent wandering through the strange and beautiful truths that science keeps uncovering. There's a small button somewhere near this video, a gentle invitation to join us again on other nights when sleep feels distant and the universe feels close. You and we're about to explore something that might sound strange at first, something you could easily dismiss as just another quirk of quantum mechanics that physicists talk about in their abstract equations. But the more we look at it, the more quietly intriguing it becomes, because what if light being in two places forever wasn't just a mathematical oddity, but a quiet doorway into understanding how the universe really constructs itself at the smallest scales? What if this strange behavior of photons was our gentle invitation to see reality not as the solid, predictable thing we imagine, but as something far more fluid, far more mysterious, far more beautiful than we ever suspected? Think about light for a moment, not the harsh glare of fluorescent bulbs or the bright flash of a camera, but the soft, ancient light that has been traveling across the universe for billions of years. Right now, as you listen to these words, photons that began their journey when the universe was young are just arriving at Earth, having crossed distances so vast that our minds can barely hold them. Each photon, each tiny packet of light, has been sailing through the darkness, never aging, never slowing, carrying within itself a story about where it came from and what it passed along the way. And yet, these same photons, these messengers from distant stars and galaxies, might not be quite what we thought they were. We've always imagined that things exist in one place at a time, that an object, whether it's a planet or a particle, occupies a single location in space. It's such a fundamental assumption that we rarely question it. Your phone is on your nightstand or in your hand, not both. The moon is orbiting Earth in one specific position at this exact moment, not spread out across multiple locations. This is how we navigate our world, how we make sense of everything around us. But when we shrink down to the scale of individual particles of light, when we enter the quantum realm where photons live and move and interact, something extraordinary happens. The rules change. Or rather, we discover that the rules we thought were universal were only approximations, comfortable simplifications that work well enough at our human scale, but dissolve like morning mist when we look closely enough. Scientists have been puzzling over this for nearly a century now, ever since the early pioneers of quantum mechanics first noticed that light seemed to behave in ways that defied common sense. They found that a single photon, when not being observed, doesn't travel along a single path like a tiny bullet shot from a cosmic gun. Instead, it exists in what physicists call a superposition, a state where it takes all possible paths simultaneously, where it exists in multiple places at once, not as a trick or an illusion, but as its fundamental nature. It's as if the photon becomes a ghost of itself, spreading out through space like a wave of probability, touching multiple locations with its phantom presence until the moment we try to measure it, to pin it down, to force it to choose. This isn't just theoretical speculation whispered in university hallways or scribbled on blackboards late at night. Scientists have demonstrated this again and again in increasingly sophisticated experiments. They send single photons through devices with multiple paths, with slits and mirrors and beam splitters, and they find that even when only one photon enters the apparatus, it somehow interferes with itself as if it travelled through all the paths at once. The mathematics that describes this is beautiful and precise, but the reality it reveals is dreamlike, almost surreal. How can something be in two places at the same time? How can a particle of light exist here and there simultaneously, without being torn apart, without violating everything we thought we knew about the nature of existence? The recent breakthrough that brings us here tonight goes even further than those early experiments. Scientists have now shown that under certain carefully controlled conditions, they can maintain this superposition, this state of being in two places, not just for microseconds or nanoseconds, but potentially indefinitely. They've created special environments, isolated from the chaos and noise of the outside world, where photons can remain in their superposed states, existing in multiple locations without collapsing into a single position. It's as if they've found a way to preserve that ghostly, spread-out nature of light, to keep it from choosing, from deciding, from becoming singular. Imagine for a moment what this means, really means, not just for our equations or our theories, but for our understanding of reality itself. Somewhere in a laboratory, perhaps right now as you're listening to these words and feeling your eyelids grow heavy, there are photons suspended in this eternal superposition, existing in two places forever, or at least for as long as the scientists can maintain their delicate experimental conditions. These particles of light are living proof that the universe doesn't always insist on the either-or choices we're familiar with. Sometimes, perhaps more often than we realize, it's perfectly content with both, and with allowing things to exist in multiple states, multiple locations, multiple possibilities all at once. The key to achieving this remarkable feat lies in something physicists call decoherence, or rather, in preventing it. You see, in our everyday world, in the warm, noisy, chaotic environment where we live and breathe and move about, quantum superpositions are incredibly fragile. The slightest interaction with the surrounding environment, a stray atom bumping into our photon, a tiny vibration in the experimental apparatus, even the faintest whisper of heat, can cause the superposition to collapse, forcing the photon to choose one location or the other. It's as if the universe is constantly asking these particles, "Where are you really?" And usually almost immediately they have to answer. They have to pick a spot and stay there. But in these new experiments, scientists have learned to create what we might call bubbles of quantum silence, regions of space so isolated, so perfectly controlled, that the universe stops asking that question. The photons can remain in their superposed state, spread out across multiple locations without being forced to choose. They use sophisticated techniques, cooling their apparatus to temperatures approaching absolute zero, where even atoms barely move, creating magnetic fields that shield their experiments from external interference, building chambers so isolated from vibration that they can detect the footsteps of someone walking down the hall 3 floors away. In these rarefied environments, something magical happens. Time seems to stretch differently for these superposed photons. While our clocks tick on, while days pass and seasons change, these particles of light remain suspended in their dual existence, neither here nor there, but somehow both. Scientists monitor them with instruments so sensitive they can detect the presence of a single photon without disturbing its delicate state, like watching a sleeping child without waking them. And what they see defies our everyday experience so profoundly that it takes time for the implications to sink in. Perhaps you're wondering why this matters, why we should care that light can be in two places forever when we have so many immediate concerns in our daily lives. But consider this: every atom in your body, every particle that makes you who you are, follows these same quantum rules at the smaller scales. The distinction between the quantum world and our classical world isn't as sharp as we once believed. It's more like a gradual transition, like watching the individual pixels of an image blur together as you step back until you can see the whole picture. What these experiments with light are showing us is that the bizarre, beautiful behavior of quantum mechanics isn't just something that happens in exotic laboratories or distant stars. It's happening everywhere, all the time, at scales too small for us to perceive directly, but fundamental to the structure of everything we see and touch and are. There's something deeply calming about knowing that at the heart of reality, things aren't as rigid as they seem. The universe allows for flexibility, for uncertainty, for possibilities that haven't yet collapsed into actualities. Every photon streaming from your bedside lamp, every particle of light that enters your eye carrying information about the world around you, has this capacity for superposition, this ability to exist in multiple states until the moment of observation. We live in a world that's constantly choosing, constantly collapsing from possibility into actuality. But these new experiments show us that, with the right conditions, we can pause that process. We can hold possibilities in suspension like notes hanging in the air after a bell has been struck. The scientists working on these experiments describe a peculiar sensation when they realize what they have achieved. Here they are, in ordinary laboratories, in ordinary buildings, in ordinary cities, and yet they've created something extraordinary. A piece of the universe that refuses to play by the classical rules, that insists on remaining quantum, remaining mysterious, remaining multiple. They've built what amounts to a time capsule for quantum weirdness, a place where the strange can remain strange indefinitely, where the impossible remains possible, where light can be in two places forever. Think about the journey of a single photon in one of these experiments. It begins its existence perhaps in a laser, created when an electron in an atom drops from a higher energy level to a lower one, releasing that packet of energy we call light. In normal circumstances, this photon would race away at the speed of light, the cosmic speed limit, interacting with mirrors and lenses and detectors until it's absorbed. Somewhere, its journey complete. But in these special setups, something different happens. The photon enters a carefully prepared quantum system, perhaps passing through a beam splitter that sends it along two paths simultaneously. Now, in our everyday understanding, we'd expect the photon to choose one path or the other, like a person at a fork in the road. But quantum mechanics tells us, and experiments confirm, that the photon takes both paths. Not half of it on each path, not a probability of being on one path or the other, but the whole photon, complete and undivided, traveling along both paths at the same time. It's as if the photon exists in a parallel universe, where both choices are simultaneously real, where the fork in the road doesn't force a decision, but allows for a kind of quantum indecision that's perfectly valid, perfectly real, perfectly natural. As the photon travels these dual paths, maintaining its superposition, it carries with it all the properties we associate with light, its frequency, determining its color if it were visible, its polarization, the orientation of its electromagnetic wave, its phase, the position in its wave cycle. All of these properties exist in superposition too, spread out across both paths, creating an intricate pattern of quantum information that somehow remains coherent, organized, meaningful, even while being fundamentally undecided about where it actually is. The experimental apparatus that maintains this superposition is a marvel of modern engineering. Every surface must be perfectly reflective, every measurement precisely calibrated, every source of noise identified and eliminated. The scientists speak of their setups with the kind of reverence usually reserved for works of art, because in a sense that's what they are. Elaborate sculptures designed not for aesthetic beauty but for quantum purity, for creating spaces where the normal rules of reality can be gently suspended. Inside these experimental chambers, time seems to flow differently. While the superposed photons remain in their dual state, existing in two places forever, or at least as long as the experiment continues, the outside world carries on with its classical certainties. It's as if there are two kinds of time running in parallel: our familiar time where things happen in sequence, where causes lead to effects, where objects move from one place to another, and quantum time where all possibilities coexist, where sequences can run backward and forward, where causality becomes fluid and negotiable. Some physicists have begun to wonder whether this ability to maintain superposition indefinitely might tell us something profound about the nature of time itself. Perhaps time as we experience it, as a one-way flow from past to future, is merely a consequence of decoherence, of quantum systems constantly collapsing from superposition into definite states. In regions where superposition can be maintained, where decoherence is prevented, time might not flow in the same way. It might eddy and swirl like water in a quiet pool, or it might not flow at all, existing instead as a kind of eternal present, where all possibilities remain perpetually open. This brings us to one of the most fascinating aspects of these experiments, the role of observation. You've probably heard of the famous thought experiment called Schrödinger's cat, where a cat in a box is supposedly both alive and dead, until someone opens the box to look. The experiments with photons in eternal superposition are like creating Schrödinger's box but never opening it, or rather, learning to peek inside without disturbing what's there. Scientists have developed techniques called weak measurements that allow them to gather information about the quantum state without fully collapsing it, like listening to someone's breathing to know they're asleep without waking them. These weak measurements reveal something remarkable. The photons in superposition aren't just passively existing in two places, they're actively maintaining complex patterns of interference, creating standing waves of probability that ripple through space like frozen music. If you could see these patterns, they might look like the intricate frost patterns that form on windows on cold nights, or like the ripples on a pond that's somehow been paused mid-splash, captured in a moment of perfect stillness that extends indefinitely. The mathematical description of these eternal superpositions involves some of the most beautiful equations in physics. They speak of wave functions that refuse to collapse, of probability amplitudes that maintain their complex phases indefinitely, of quantum states that exist in what physicists call Hilbert space, an abstract mathematical realm with infinite dimensions where every possible state of every possible particle has its own coordinate. It's a space that our brains aren't equipped to visualize directly, but mathematics allows us to navigate it, to make predictions, to understand what's happening even when we can't picture it. As we drift deeper into this quantum realm, it's worth pausing to consider what we mean when we say a photon is in two places forever. Forever is a word we use casually, but in physics, it carries weight. It means that given perfect isolation, perfect protection from decoherence, there's no internal mechanism that would cause the superposition to decay. It's not like a battery running down or a spinning top gradually slowing. The superposition is a stable state, as natural and sustainable as a planet's orbit or an electron's spin. Of course, in practice, forever is limited by our ability to maintain those perfect conditions. Even the best isolated systems eventually interact with their environment in some tiny way. A cosmic ray passing through the laboratory, a minute vibration from a distant earthquake, even the gravitational waves from colliding black holes billions of light years away could potentially disturb the delicate superposition. But the fact that we can maintain it for any significant length of time, that we can create these pockets of quantum stability in our noisy, chaotic world, is itself a kind of miracle. The implications of this work extend far beyond the laboratory. If we can maintain quantum superpositions indefinitely, we might be able to build quantum computers that can solve problems currently beyond our reach, exploring vast solution spaces simultaneously rather than checking possibilities one by one. We might develop new forms of communication, where information exists in superposition, neither sent nor unsent until the moment it's needed. We might even find ways to put larger objects into superposition, gradually bridging the gap between the quantum and classical worlds until the distinction dissolves entirely. But perhaps the most profound implication is philosophical. These experiments force us to confront the nature of reality itself. If a photon can be in two places forever, what does it mean to be in a place? If observation collapses superposition, what exactly is observation? Is consciousness required, or is any physical interaction sufficient? These aren't new questions. Physicists and philosophers have been debating them since quantum mechanics was first discovered, but each new experimental achievement like this one sharpens the questions, makes them more urgent, more real. Some researchers have suggested that superposition might be the fundamental state of reality and what we call classical physics. The world of definite positions and deterministic motion might be the exception rather than the rule. Perhaps the universe is naturally quantum, naturally uncertain, naturally multiple, and it's only the constant interaction between particles, the endless network of observation and measurement that happens automatically at every scale, that creates the illusion of classical certainty. We see the world as solid and definite not because it is, but because we can't help but observe it, and observation always collapses superposition. This view turns our usual understanding upside down. Instead of quantum mechanics being the weird exception that happens at tiny scales, classical mechanics becomes the weird exception that happens when quantum systems can't maintain their isolation. The natural state of light, and perhaps of everything, is to be in multiple places, to exist in superposition. It's only the messy, noisy, interconnected nature of our macroscopic world that forces things to choose, to be in one place at a time. As you lie there in the darkness, perhaps feeling yourself beginning to drift towards sleep, consider that the photons streaming from distant stars, traveling across the vast emptiness of space, might be maintaining their superpositions for millions or billions of years. In the vacuum between galaxies, where there's nothing to interact with, nothing to cause decoherence, light might naturally exist in two places, or many places, throughout its entire journey. Only when it finally reaches something, a telescope, a planet's atmosphere, your eye, does it finally have to choose where it is. This means that the night sky might be even stranger than we imagined. Each star we see might be sending us photons that existed in superposition for eons, exploring every possible path through space, every possible route around intervening galaxies and dark matter, before finally choosing the path that leads to us at the moment of observation. The light we see isn't just old, it's quantum old, carrying with it not just information about its source, but about all the possibilities it explored along the way. The experimental techniques that allow scientists to maintain these eternal superpositions are constantly improving. What started as fleeting glimpses of quantum behavior lasting microseconds has extended to milliseconds, seconds, and now potentially indefinitely. Each improvement requires new innovations, better isolation, cleverer measurement techniques, deeper understanding of how decoherence works and how to prevent it. It's like learning to hold a soap bubble intact not just for seconds but for hours, days, forever, protecting it from every breeze, every temperature change, every vibration that might pop it. The laboratories where this work happens are temples of precision. Everything must be controlled. The temperature, kept within billionths of a degree of absolute zero. The magnetic fields, shaped with superconducting coils to create perfectly still regions of space. The vibrations, dampened with elaborate suspension systems that isolate the experiment from the building, from the ground, from the entire planet's constant trembling. Even the air is removed, creating vacuums more perfect than the emptiness between stars. In these pristine environments, researchers can observe phenomena that would have seemed like magic to scientists just a generation ago. They watch as photons interfere with themselves, creating patterns that prove they were in two places at once. They see quantum correlations that persist indefinitely, connections between particles that remain perfectly synchronized even when separated, as if they were two parts of the same thing rather than distinct objects. They measure properties that exist only in superposition, that have no classical equivalent, that can't even be described without the mathematics of quantum mechanics. The photons in these experiments aren't special in any way. They're identical to the photons produced by your reading lamp, by the sun, by every light source in the universe. What's special is the environment, the carefully crafted conditions that allow their quantum nature to persist without interruption. It's as if these scientists have created windows into the quantum realm, places where we can see reality as it really is when we're not looking, when our observation isn't forcing it to choose, to decide, to collapse into the familiar classical world. This work has practical applications that are already beginning to emerge from laboratories. Quantum sensors that use superposition to detect impossibly faint signals, measuring gravitational waves or magnetic fields with precision that classical instruments could never achieve. Quantum communication systems that use the fragility of superposition as a feature, creating messages that can't be intercepted without destroying them, providing perfect security through the laws of physics rather than through encryption. Quantum computers that use superposition to explore multiple solutions simultaneously, potentially solving problems that would take classical computers longer than the age of the universe. But beyond these applications, there's something deeply satisfying about knowing that we can touch the quantum world so directly that we can create conditions where its strange rules become visible, tangible, measurable. We're not just theorizing about photons being in two places. We're making it happen, maintaining it, studying it. We're learning to speak the language of quantum mechanics not just in equations but in experimental reality. As the night deepens around you, as your breathing slows and your thoughts begin to soften and blend, consider that you yourself are made of particles that obey these same quantum rules. The electrons in your atoms, the photons carrying energy through your cells, the very molecules that make up your DNA, all of them have this capacity for superposition, for existing in multiple states simultaneously. At the smallest scales, you aren't purely classical any more than light is. You're quantum too, participating in the same beautiful uncertainty that allows photons to be in two places forever. The boundary between the quantum and classical worlds isn't a sharp line, but a gradual transition. As objects become larger, as they contain more particles, as they interact more with their environment, superpositions become harder to maintain. But there's no fundamental law that says where quantum behavior must stop and classical behavior must begin. Some physicists have proposed that even macroscopic objects, perhaps even living things, might maintain quantum superpositions under the right conditions. We don't know where the limit is, or if there even is a limit. Recent experiments have pushed this boundary further than ever before. Scientists have put viruses into superposition, tiny but undeniably complex biological entities existing in multiple states simultaneously. They've created superpositions of mechanical oscillators, tiny tuning forks that vibrate in two different modes at once. They've even proposed experiments that might put larger objects, things visible to the naked eye, into quantum superposition. Each success pushes our understanding, further challenges our assumptions about what's possible, what's real, what's fundamental. The idea that light can be in two places forever also connects to deeper mysteries in physics. It touches on questions about the nature of space itself. If a photon can be in two places, what exactly is a place? Is space a kind of container that holds things, or is it something that emerges from the relationships between things? Quantum mechanics suggests the latter, that space might not be fundamental but emergent, arising from quantum entanglement and superposition, rather than existing independently. This connects to ideas in quantum gravity, the attempt to understand how quantum mechanics and general relativity fit together. Some theories suggest that space itself might be in superposition at the smallest scales, that the fabric of reality might be quantum, uncertain, multiple. The photons in these experiments might be revealing something not just about light, but about the nature of space and time themselves. There's also a connection to the many worlds interpretation of quantum mechanics, the idea that every quantum superposition represents a branching of reality, that all possibilities are actually realized in parallel universes. In this view, when we say a photon is in two places forever, we might be saying that there are two universes, each containing the photon in a different place, and these universes remain parallel, unobserved, uncollapsed, as long as the superposition persists. The experiments that maintain superposition indefinitely might be maintaining these parallel realities, keeping them from merging or selecting just one. This interpretation is controversial. Not all physicists accept it, but it illustrates how these experiments push us to think about reality in fundamentally new ways. Whether you prefer to think of superposition as multiple possibilities or multiple realities, the experimental facts remain the same. We can create conditions where light exists in two places, not momentarily but persistently, not approximately but exactly, not theoretically but measurably. As we continue to explore these quantum phenomena, we're also discovering that superposition is just one aspect of a broader quantum reality. Entanglement, where particles remain connected regardless of distance. Tunneling, where particles pass through barriers they shouldn't be able to cross. Vacuum fluctuations, where particles pop into and out of existence in empty space. All of these phenomena are facets of the same underlying quantum nature that allows light to be in two places forever. The universe, it seems, is far more flexible than our everyday experience suggests. At its foundation, reality is not made of solid, definite things in specific locations, but of possibilities, probabilities, potentials that haven't yet decided what to become. The classical world we experience, where things have definite properties and locations, emerges from this quantum foundation through the process of observation, measurement, interaction. But that emergence isn't inevitable or necessary. It's contingent, dependent on circumstances, and as these experiments show, avoidable under the right conditions. This flexibility of reality might seem unsettling at first, but there's something deeply peaceful about it too. It means the universe isn't rigid, isn't deterministic in the clockwork way that classical physics suggested. There's room for possibility, for potential, for things to be genuinely uncertain and open. Every photon of light, every particle in your body, every atom in the stars, carries within it this capacity for multiplicity, for existing in more than one state, for being more than one thing. The scientists who work with these eternal superpositions often speak of a kind of quiet awe that comes over them in the laboratory. Here they are, using lasers and mirrors and detectors, ordinary equipment you might find in any physics department, and yet they're touching something profound, something that challenges our most basic assumptions about reality. They're not just observing the universe, they're coaxing it to reveal its quantum nature, to show them what light really is when it's not being forced to pretend to be classical. The delicate dance of maintaining superposition requires constant vigilance. Temperature fluctuations of a billionth of a degree can destroy it. Vibrations smaller than the width of an atom can cause decoherence. Even the gravitational pull of a person walking by can potentially disturb the quantum state. It's as if the classical world is constantly trying to assert itself, to force the quantum system to choose, to collapse, to become definite. But with sufficient care, sufficient isolation, sufficient understanding, we can hold it at bay. We can preserve the quantum indefinitely. This preservation isn't passive. It requires active intervention. Physicists use techniques like dynamical decoupling, sending precisely timed pulses of energy to counteract environmental effects. They use error correction, constantly monitoring the system and making tiny adjustments to maintain the superposition. They use topological protection, arranging the quantum states in ways that are naturally resistant to certain types of disturbance. It's like keeping a bubble intact, not by protecting it from all forces, but by carefully balancing the forces so they cancel out. The energy required to maintain these quantum states is surprisingly small. Once a photon is in superposition, it doesn't take continuous energy input to keep it there, only the energy needed to maintain the isolation, the cooling, the protection from decoherence. The superposition itself is a natural state, as stable as any classical configuration. This suggests that the universe might be full of natural quantum superpositions that we simply haven't noticed because we haven't looked in the right way or in the right places. Consider the interior of neutron stars, where matter is compressed to densities that exist nowhere else in the universe. In those extreme conditions, particles might naturally maintain superpositions, existing in multiple states simultaneously. Or consider the cosmic voids, the vast empty spaces between galaxy clusters where particles might travel for millions of years without interacting with anything. These could be natural laboratories where quantum superposition persists on scales and timescales that dwarf our earthly experiments. Even in our own bodies, there might be quantum superpositions we haven't yet detected. Some researchers have suggested that certain biological processes like photosynthesis or bird navigation, or perhaps even consciousness itself, might involve quantum superposition. The warm, wet, noisy environment of living cells seems hostile to quantum effects, but life has had billions of years to evolve mechanisms that might protect and utilize quantum phenomena. We're only beginning to explore these possibilities. The philosophical implications of eternal superposition extend to questions of identity and existence. If a photon can be in two places forever, is it one photon or two? Does it have a single identity that's somehow spread out, or does it exist as multiple versions of itself? These questions don't have easy answers, and different interpretations of quantum mechanics suggest different resolutions. But the experimental facts force us to confront these questions, to recognize that our intuitive notions of identity and existence might be too limited to describe quantum reality. There's also the question of information. When a photon is in superposition, it carries quantum information that doesn't exist in classical physics. This information isn't just about where the photon might be found if measured, but about the complex relationships between its possible states, the phases and amplitudes that determine how it will interfere with itself or with other quantum systems. This quantum information can be processed, transmitted and stored in ways that classical information cannot, opening up entirely new possibilities for technology and perhaps for understanding the universe itself. Some physicists have proposed that information, not matter or energy, might be the most fundamental aspect of reality. In this view, particles like photons are just excitations in quantum information fields, and properties like position and momentum are just different ways of encoding information. The ability to maintain superposition forever might then be understood as the ability to preserve quantum information indefinitely. to create permanent records written not in stone or silicon, but in the fabric of quantum reality itself. As you continue to drift towards sleep, feeling perhaps that boundary between waking and dreaming beginning to blur, you're experiencing your own kind of superposition. Your consciousness exists in a state that's neither fully awake nor fully asleep, maintaining multiple possibilities, multiple streams of thought, multiple interpretations of the sounds and sensations around you. Perhaps this is the closest our macroscopic minds can come to experiencing what it's like to be a photon in eternal superposition, existing in multiple states without having to choose. The research into eternal superposition continues to advance. Each month brings new publications, new techniques, new records for how long superposition can be maintained and under what conditions. Scientists are exploring different physical systems, not just photons, but atoms, molecules, even tiny mechanical devices. They're finding that superposition is more robust than we thought, that it can survive conditions we assumed would destroy it, that it might be maintained using principles we're only beginning to understand. One particularly intriguing direction involves using topology, the mathematics of shapes and spaces, to protect quantum states. By encoding quantum information in topological properties that can't be changed by small disturbances, scientists hope to create superpositions that are naturally stable, that maintain themselves without active intervention. It's like tying a knot that can't be untied without cutting the rope. The quantum state becomes locked into superposition by the very structure of the system. Another approach involves using quantum error correction, borrowed from the field of quantum computing. By encoding a single quantum state across multiple physical particles, scientists can detect and correct errors without destroying the superposition. If one particle begins to decohere, the others can pull it back into line, maintaining the overall quantum state indefinitely. It's like having multiple backup copies that constantly check and reinforce each other, but at the quantum level where the copies can exist in superposition themselves. These technical advances are bringing us closer to practical applications that seemed like science fiction just a few years ago. Quantum memories that can store information in superposition indefinitely, preserving not just data, but the quantum correlations that make quantum computing powerful. Quantum sensors that can maintain coherent superposition for hours or days, accumulating signals too faint to detect in shorter times. Quantum networks that can maintain entanglement across global distances, creating unhackable communication channels that rely on the laws of physics for their security. But perhaps the most exciting possibility is that we're approaching the ability to put truly macroscopic objects into superposition. There's no fundamental law that says superposition must be limited to microscopic particles. The challenges are practical, not theoretical. How to isolate large objects from their environment, how to cool them to quantum ground states, how to measure them without destroying their quantum properties. Each breakthrough with photons and atoms brings us closer to solving these challenges. Imagine a world where macroscopic superposition is possible and controllable. Objects could exist in multiple locations simultaneously, not just in abstract quantum experiments, but in practical applications. Transportation might involve putting objects into superposition, having them exist at both the origin and destination, then collapsing the superposition to complete the journey instantly. Manufacturing might involve superposing different possible configurations of atoms and selecting the best one. Even medicine might use superposition to explore multiple treatment pathways simultaneously. These possibilities might seem fantastical, but they follow logically from what we're already demonstrating with photons. If light can be in two places forever, if we can maintain and control that superposition, then the same principles might apply to any physical system given the right conditions. The boundary between quantum and classical isn't a wall, but a frontier, and we're pushing it back experiment by experiment, photon by photon, discovery by discovery. As the night continues to deepen, as your thoughts become softer and more dreamlike, consider that the universe itself might have begun in a state of superposition. Some cosmological theories suggest that the Big Bang wasn't a single event, but a superposition of all possible beginnings, and what we call our universe is just one branch of that primordial superposition. Other branches might have collapsed differently or might still exist in parallel, maintaining their superposition for billions of years. This connects to ideas about the multiverse, about parallel realities, about the fundamental nature of existence itself. But even if we set aside these speculative ideas, the confirmed fact remains. We can put light into superposition and keep it there indefinitely. We can create pockets of quantum reality that persist in our classical world. We can touch the strange and beautiful foundations of existence with our experiments, our instruments, our understanding. The photons in these eternal superpositions aren't doing anything dramatic. They're not exploding or radiating energy or sending messages to distant galaxies. They're simply existing, quietly, peacefully, in two places at once, demonstrating that reality is far more flexible and mysterious than our everyday experience suggests. They're proof that the universe allows for possibilities we're only beginning to explore, for states of being that transcend our classical intuitions, for a kind of existence that's neither here nor there but somehow, impossibly, both. And in this quiet demonstration, in this gentle insistence on being in two places forever, these photons are teaching us something profound about the nature of reality. They're showing us that the solid, definite world we experience is just one way reality can be, not the only way. They're revealing that beneath the surface of classical certainty lies a quantum realm of infinite possibility, where the rules are different but not arbitrary, strange but not chaotic, mysterious but not unknowable. The scientists who first predicted quantum superposition could barely have imagined that we'd one day be able to maintain it indefinitely, to create conditions where quantum mechanics isn't just a fleeting glimpse but a persistent reality. Yet here we are in the early 21st century, routinely creating and maintaining states that would have seemed miraculous to Einstein, Bohr, Schrödinger, and the other pioneers of quantum mechanics. We're not just understanding the quantum world, we're learning to inhabit it, to make it our own, to use its strange properties for our purposes. This is perhaps the most remarkable aspect of the whole endeavor, that beings made of classical matter, living in a classical world, thinking with classical brains, have somehow discovered and learned to manipulate the quantum foundation of reality. We've reached down through the scales of existence to touch the level where things can be in two places forever, and we've brought that knowledge back up to our scale, encoded it in our equations, demonstrated it in our laboratories, begun to build technologies around it. The future possibilities are limited only by our imagination and ingenuity. As we get better at maintaining superposition, at protecting quantum states from decoherence, at scaling up from single photons to larger systems, we'll discover new phenomena, new applications, new ways of understanding and interacting with reality. The photons that today exist in two places forever in specialized laboratories might tomorrow be part of everyday technologies we haven't yet imagined. But even if these practical applications never materialize, even if eternal superposition remains a laboratory curiosity, its mere existence has already changed our understanding of reality in fundamental ways. We know now that the classical world is not inevitable, that quantum mechanics is not just a mathematical formalism, but a genuine description of how things can be. We know that light, that most familiar and essential phenomenon, carries within it mysteries that we're only beginning to unravel. As sleep finally begins to claim you, as your own thoughts begin to superpose and interfere and create the strange landscapes of dreams, remember that you're surrounded by light that has the capacity to exist in multiple places, by particles that follow quantum rules even when forced to appear classical, by a universe that's far stranger and more wonderful than it appears. The photons streaming from distant stars, the ones that left their sources millions of years ago and traveled through the vast emptiness to reach Earth tonight, might have maintained their superpositions for most of that journey, existing in multiple states across cosmic distances until the moment they reached our atmosphere and were forced to choose where to be. Every piece of light that touches you carries this potential for quantum strangeness, this ability to transcend the either-or logic of classical physics and embrace the both-and logic of quantum mechanics. You're bathed in quantum possibilities that collapse into classical actualities only at the last possible moment, only when observation makes them choose. The room around you, dark as it might be, is crisscrossed with photons exploring multiple paths, existing in multiple places, maintaining superpositions until they interact with something that forces them to decide. And somewhere, in laboratories around the world, scientists are working through the night, maintaining their delicate experiments, keeping photons in eternal superposition, pushing the boundaries of what we thought was possible. They're the explorers of our age, Not crossing oceans or climbing mountains, but navigating the quantum realm, mapping territories that exist in mathematical spaces, discovering new ways that reality can be. Their work is quiet, meticulous, often frustrating, but occasionally brilliantly successful in revealing something new about the universe. These revelations don't come with fanfare or explosions. They come as subtle shifts in interference patterns, as barely perceptible changes in detector readings, as statistical accumulations that slowly reveal quantum truths. The photons being held in superposition don't announce their strange state. They simply exist, quietly demonstrating that our intuitions about reality are limited, that nature is more creative than we imagined, that possibilities we never considered are not just theoretically allowed, but practically achievable. The mathematics that describes these eternal superpositions is a language that few people speak fluently, but its poetry is universal. It tells of waves that never collapse, of possibilities that never resolve, of states that exist in perfect balance between being and becoming. It describes a universe where information can exist without definite form, where properties can be possessed without being determined, where existence itself becomes a more fluid and flexible concept than our macroscopic experience suggests. In the equations, photons dance between possibilities, their wave functions spreading and interfering, creating patterns of probability that ripple through abstract spaces. The mathematics doesn't tell us what a photon is exactly, but it tells us how it behaves, what we can expect, what we can measure. And what it tells us is that photons, and by extension all quantum particles, don't fit into the neat categories our minds create. They're neither purely waves nor purely particles, neither definitely here nor definitely there, neither completely real nor completely potential. This ambiguity isn't a flaw in our understanding or a limitation of our instruments. It's a fundamental feature of reality at the quantum scale. The universe doesn't insist on definite answers to all our questions. Some questions, like, where exactly is this photon, don't have single answers unless we force them to by measuring, by observing, by interacting. Left alone, protected from decoherence, photons are content to exist in superposition indefinitely, embodying multiple answers simultaneously. The transition from quantum to classical, from superposition to definite states, from multiple possibilities to single actualities, is still one of the deepest mysteries in physics. We know how to calculate when it will happen, how to prevent it or encourage it, how to use it for our purposes, but we don't fully understand why it happens, what exactly constitutes a measurement, why the universe seems to have two different sets of rules for quantum and classical scales. Some physicists think there's no real distinction, that everything is quantum and classical physics is just an approximation that emerges statistically when huge numbers of quantum particles interact. Others believe there's a genuine collapse mechanism, something that forces quantum superpositions to resolve into classical states when they reach a certain size or complexity. Still others, following the many worlds interpretation, argue that superposition never really collapses. Reality just branches, and we only experience one branch. These debates continue in conferences and journals, in late-night discussions and blackboard calculations. But while theorists argue about interpretations, experimentalists continue pushing the boundaries, creating longer-lasting superpositions, larger quantum systems, more precise control over quantum states. Each success adds another piece to the puzzle, another constraint that theories must satisfy, another hint about how reality really works. The ability to maintain photons in superposition forever, or at least for arbitrarily long times, represents a kind of mastery over quantum mechanics that would have seemed impossible just decades ago. We've gone from merely observing quantum phenomena to actively creating and controlling them. We're not passive students of the quantum world anymore. We're becoming quantum engineers, quantum architects, quantum artists creating states of light that embody the deepest mysteries of physics. This mastery brings with it a responsibility to think carefully about what we're doing and why. As we develop quantum technologies based on eternal superposition, we need to consider their implications not just for science and technology, but for society, for philosophy, for our understanding of our place in the universe. These aren't just abstract scientific questions. They touch on fundamental issues of reality, knowledge, existence, and possibility. The photons we hold in superposition are ambassadors from the quantum realm, bringing messages about how reality works at its most fundamental level. They tell us that nature is not constrained by our classical intuitions, that there are ways of existing we never imagined, that the universe is far more creative and flexible than we thought. They remind us that we're still at the beginning of our journey to understand reality, that there are mysteries remaining that might take centuries to unravel. But they also tell us that these mysteries are not impenetrable, that with patience and ingenuity and careful experimentation, we can learn to speak the quantum language, to participate in the quantum dance, to create and maintain states that seemed impossible. Every photon we keep in a superposition is a small victory over classical limitations, a tiny demonstration that we can touch and manipulate the quantum foundations of reality. As your consciousness continues to fade towards sleep, as the boundaries between waking and sleeping, between conscious and unconscious, between here and there begin to blur, you're experiencing something that might not be entirely different from quantum superposition. Your thoughts exist in multiple states. Your awareness spreads across possibilities. Your dreams begin to interfere with your waking perceptions. You're entering a state where the classical logic of daytime thinking gives way to something more fluid, more multiple, more quantum-like. Perhaps consciousness itself involves quantum processes, perhaps the ability to hold multiple thoughts simultaneously, to consider different possibilities, to imagine what isn't but could be, relies on the same quantum principles that allow photons to be in two places forever. We don't know yet. The relationship between quantum mechanics and consciousness remains one of the deepest mysteries. But as we learn to create and maintain quantum superpositions, as we explore what's possible at the quantum scale, we might be approaching an understanding of our own minds as well as the universe around us. The photons in eternal superposition are showing us that reality is not a fixed stage where classical actors play out deterministic scripts. It's more like an improvisational performance where possibilities remain open, where multiple storylines can coexist, where the ending isn't determined until the final observation. We're not just observers of this performance, we're participants, our measurements and interactions helping to shape which possibilities become actualities. This participatory universe, where observation plays a fundamental role in determining what becomes real, challenges our assumptions about objectivity and subjectivity, about the relationship between observer and observed, about the nature of scientific knowledge itself. We're not discovering a reality that exists independently of our investigations. We're co-creating reality through our experiments, our measurements, our decisions about what to observe and how. But this doesn't mean reality is arbitrary or subjective. The rules of quantum mechanics are precise and unforgiving. We can't make photons do whatever we want. We can only work within the possibilities that quantum mechanics allows. The superpositions we create must respect conservation laws, uncertainty principles, and all the other constraints that govern quantum systems. We're partners with nature, not masters of it, learning to dance with quantum possibilities rather than forcing them to conform to our wishes. The laboratories where eternal superpositions are maintained have become temples of quantum reality, places where the normal rules are suspended and different laws apply. The scientists who work there speak of a kind of reverence that comes from daily contact with quantum phenomena, from seeing with their own instruments what was once only mathematical abstraction. They're witnesses to the fact that our universe is quantum at its core, that the classical world we experience is the exception, not the rule. As more laboratories achieve the ability to maintain eternal superpositions, as the techniques become more refined and accessible, we're approaching a tipping point where quantum technologies might become as common as classical ones. The photons that today require entire buildings full of equipment to maintain in superposition might tomorrow be controlled by devices that fit on a chip, that operate at room temperature, that integrate seamlessly with classical systems. This quantum revolution won't happen overnight. There are enormous technical challenges to overcome, fundamental physics to understand, engineering problems to solve. But the fact that we can maintain any superposition indefinitely, that we've crossed that threshold from temporary to permanent quantum states, suggests that these challenges are surmountable. We're not fighting against nature but learning to work with it at its deepest level. The implications extend beyond technology to our fundamental worldview. As quantum phenomena become more visible and controllable, as eternal superposition becomes a practical tool rather than a laboratory curiosity, our culture will have to assimilate these ideas. Children might grow up with quantum intuitions that seem as natural to them as classical mechanics seems to us. The idea that things can be in multiple places, that observation changes reality, that possibility is as fundamental as actuality, might become part of our common understanding. But for now, for tonight, it's enough to know that somewhere, in carefully controlled chambers, photons are demonstrating the impossible. They're existing in two places forever, neither here nor there, but somehow both, carrying within their superposed states all the mystery and beauty of quantum mechanics. They're proof that the universe is stranger than we imagined, more flexible than we assumed, more wonderful than we dared hope. These photons don't care about our debates and interpretations. They simply exist, following the quantum rules that govern all particles at the smallest scales, demonstrating by their very existence that reality is not what it seems. They're patient teachers, waiting in their superposed states for us to understand, to appreciate, to utilize the possibilities they represent. They're showing us that forever doesn't have to mean unchanging, that eternal can coexist with uncertain, that permanent can still be multiple. The research continues, the boundaries keep expanding, the impossible keeps becoming possible. Each day brings new insights, new techniques, new ways to create and maintain quantum superpositions. We're writing the next chapter in humanity's understanding of reality, one photon at a time, one experiment at a time, one breakthrough at a time. And at the heart of it all are these simple particles of light, demonstrating with quiet insistence that they can be in two places forever. As sleep finally takes you, as your consciousness dissolves into dreams where the normal rules don't apply, where you can be in multiple places, experience multiple realities, exist in superposition between different states of being, remember that this isn't just fantasy or imagination. It's a reflection of the deeper reality that physics has revealed, a reality where photons lead the way into a quantum future we're only beginning to imagine. The universe whispers its secrets through these superposed photons, telling us stories about the nature of existence that we're still learning to hear. They speak of possibilities that don't collapse, of states that don't choose, of realities that coexist without conflict. They show us that the either-or world of classical physics is just one melody in a vast quantum symphony where notes can be played simultaneously, where harmonies emerge from superposition, where the music never has to resolve to a single key. Tonight, while you sleep, photons will continue their eternal dance in laboratories around the world. Scientists will monitor their equipment, adjust their parameters, and maintain the delicate conditions that allow superposition to persist. They'll gather data that confirms what we already know and hints at what we don't yet understand. They'll push the boundaries a little further, make the impossible a little more possible, bring the quantum future a little closer, and throughout the universe, natural superpositions will persist in places we haven't yet imagined. In the cold depths of space, in the hearts of exotic stars, in the quantum vacuum itself, photons and other particles will maintain their multiple states without any help from us, following the quantum rules that govern reality at its foundation. We're not creating something artificial when we maintain eternal superposition. We're revealing something that was always there, waiting to be discovered, waiting to be understood. The photons don't distinguish between natural and artificial superposition. To them, it's all the same. The freedom to exist in multiple states, to explore multiple possibilities, to remain uncommitted to a single reality. Whether in our laboratories or in distant galaxies, they demonstrate the same beautiful principle, that the universe allows, even prefers, states of graceful uncertainty, of peaceful multiplicity, of eternal possibility. So as you drift deeper into sleep, carried by the gentle rhythm of your breathing, remember that you're surrounded by a universe where photons can be in two places forever, where the impossible is routinely achieved, where mystery and understanding dance together in the eternal superposition of knowledge and wonder. The quantum realm isn't separate from our world. It's the foundation our world is built on, the deep reality from which classical appearance emerges. And in that deep reality, in that quantum foundation, light leads the way, showing us through its eternal superpositions that existence is far richer, far stranger, far more beautiful than we ever imagined. Photons in two places forever aren't breaking the rules. They're showing us what the real rules are, the quantum rules that govern everything at the smallest scales, and perhaps, if we're patient and clever enough, at all scales. The night continues its slow journey toward dawn, but the photons in superposition don't mark time the way we do. For them, existing in multiple states, the passage of time is different, perhaps non-existent in the way we understand it. They remain suspended in their quantum states, neither arriving nor departing, neither here nor there, demonstrating with infinite patience that reality is quantum, that superposition is natural, that being in two places forever isn't impossible, but simply another way the universe expresses its fundamental nature. And as you finally surrender to sleep, as your last conscious thoughts fade into the quantum uncertainty of dreams, you become part of this vast pattern, this cosmic dance where possibility and actuality interweave, where observation and existence shape each other, where photons can be in two places forever, and that's not strange, but simply true. The universe continues its quantum whispers through the night, through your dreams, through the eternal superposition of light that surrounds and sustains us all, carrying us gently, peacefully, into the quantum depths of sleep, where all possibilities coexist and nothing has to choose, nothing has to collapse, nothing has to be in just one place when it could be everywhere, forever, in the soft eternal superposition of night. End.